Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to be further expanding our mesh implementation by loading OBJ files. So before we jump into the video, I would like to take a quick minute and thank the partners of the channel. The partners are the highest tier of support both on YouTube and Patreon, and they are Caden, Eearslya, Gerboles Inc., Kyla, Super Awesome, and Wensheng. I'd also like to thank all the other fine folks that appear on the screen here. Your support is greatly appreciated. Thank you very much. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. Okay, so today we are going to be kind of switching things up a little bit in terms of video format. So as I discussed in the video that I released on Tuesday, a link to that will be up in the corner. We are changing up the format of the series going forward. So there's going to be a lot less editing. There's just going to be straight up coding on the screen, occasional copy paste of things that don't really matter or that take a long time unnecessarily to do live here. But for the most part, we are going to be going very light on the editing. So with that out of the way, we are going to be taking a look at loading up OBJ files. So for those of you who aren't familiar with what an OBJ file is, an OBJ file is sort of an old format that's been around for 3D models, and it contains very basic information about vertices. So it does contain position, normal, and texture coordinate information, but not much else. However, it does also allow you to specify material data as well. And so we are actually going to be handling both of those things because we want to use these OBJ files to also sort of generate a material definition on the fly whenever we load one. And so we are going to have to do a little bit of generation of some data, and we are going to have to handle some things that the OBJ format just does not handle. But this is an example of some of the things that you're going to have to handle whenever you go to actually load models from disk. So OBJ is not going to be the only format that we load, of course. We're going to be supporting a lot of different formats because OBJ is fairly limited in what it supports. For one thing, it doesn't support animation or skeletal systems of any kind. And so the reason I chose this one is because it is a very sort of readable format. It's human readable. It's not binary. It's just straight up text in a file. And so that makes it really easy for us to visualize what's going on for our first loader that we're going to be loading in this series. Our first loader that we're going to be developing in the series, rather. And so what we're going to do is take a quick look at some of the assets that we're going to be importing. I have a couple of examples that I'm going to use. The first one is just a more simplistic example of a OBJ that just contains a lot of data, but there's not really a whole lot to it. And then the second one is going to be a more complex example of an OBJ that contains lots of objects and lots of materials. So the first thing before we actually get into any of the code is we need to make a couple of changes here with our files. So we are going to have a new type of asset. So I'm just going to create a new folder here, and we're going to call this models. And this is where our OBJ files are going to exist. So for now, I'm just going to bring these in from an outside folder. So we have our Vulkan OBJ and our Vulkan MTL. Now these are just something I picked up from somewhere on the internet. I don't intend on using these for all that long. It's really just a test case for us, right? So these assets are, I don't recall where they came from, to be quite honest with you, but they're good examples to sort of work against. So we're going to be using this, and then we're also going to be using a OBJ version of the Sponza scene. So with that, let's go ahead and take a quick look at what an OBJ looks like. So I'm actually going to open this with, in my case, I think I'll use Kate to open this. Let me just close my other documents that I have open there. Let me see, can I move this to a different window actually? I think that I can. No. All right, whatever. So if we expand this, this is a OBJ file that was exported from Blender. And there is a version of this that works from 3D Studio Max as well. However, that format is a little bit different than this one. And so I can't guarantee that that will work. So we're going to use the one that's exported from Blender. And I may eventually expand on the logic here to get that other one to work. But for now, it's not really important because Blender is free. Everybody has access to that as opposed to 3D Studio Max, which is not free and decidedly expensive. So the basic format that we're looking at here is the very first thing that it defines is a material library. And that is an MTL file that contains all of our material definitions that are going to be used by all of our objects in this OBJ scene. So we'll circle back around to that in a minute. The next thing we have here is if we look at the first letter of each line, we can kind of determine what data that line is going to contain. So here we have an M. That's most likely going to contain material library information. Here we have an O that defines the start of a new object. So we have a new object. It's named plane.plane.001 or plane_plane001. Don't ask me why they named it that, but that's what its name is. And then we have a whole bunch of lines here with V, and these are vertex positions. So this is the position in space. So we have X here, and then we have Y here, and then we have Z here. Okay, and these have been exported in Blender using the Y up scheme. So it's oriented correctly for us already out of the box. So we have all of this vertex information. And if we scroll down a little bit, I'm just going to do this real quickly because as you can see, there are lots of them. So when we get down here, we have another line called VT. So this means that anytime we have a line that starts with V, we're actually going to have to look at the next character to see what kind of data we're looking at. So start thinking about that as we're going through this file. So VT is texture coordinates. So we just have two elements here. We have an X and we have a Y. And that's really all there is to that. It's pretty simple and straightforward. So I'm actually going to scroll down a little bit further to the next section. Looks like I went a little bit too far here. Okay, and this is to a section of VN records. And as you might have guessed, that is vertex normals. So these are the normals for each individual vertex. So all of these things line up. So there are the exact same amount of vertex positions, texture coordinates, and normals that all line up and can be put into a single vertex structure. So it lines up sort of with the data that we already have, the data structure that we already have. And so this gives us pretty much everything that we're going to need to know about the individual object. So if I scroll down a little bit further down past this, we have a couple more things here. So that is all of our vertex information for the current object. The next thing that we have is a line that starts with U, which is use material. So this uses a material by name, which also nicely lines up with what we're going to do. Because these materials are referenced by name, and our material system also references materials by name. That wasn't an accident. This will line up nicely with what we are going to do. So when we go ahead and parse that material file, we're also going to have a material in our system to line up with the name here. So this just tells us what material should be used for the current object. S is for smoothing groups. We are actually not really going to use this right now. This is another way to sort of split multi-sub objects because you can technically have a different material used per one of those. We're not actually going to do that right off the bat. Again, that's something that we can support later, but we're trying to keep this simple for now. And then we have a bunch of F records. And these Fs are faces, as you might have guessed. So what these have are indices on them for the position, texture coordinate, and normal. And the nice part about this is that it automatically indexes into these massive arrays of data that we already have. And that tells us 3 individual vertices for a particular triangle. So we now have triangle information, which we also can use directly within our system, because our engine actually uses triangles to render everything. So again, this lines up nicely. I should point out that OBJ can export quads, but we are not going to be dealing with quads. So if you export quads, it's not going to work very well, if at all. So we've exported this by triangulating the mesh, and that is the data we have here. So that is all we're going to be looking at. So we have all these faces, and as you can see, there are quite a lot of them. The other thing that I should point out is, before I move on, actually, so let me go, it's a little further up. These faces are 1 indexed versus most computer languages out there, which treats arrays as 0 indexed. So we're going to have to keep that in mind as well, that we don't actually want to start with index 1. When this says 1, it actually means 0, meaning the first element in the array. So we're going to have to subtract 1 at various parts throughout our code to actually compensate for that. So that is the face information. And as you can see here, that is where the file ends. So this is not a particularly complicated object, but you can see that it has over 22, almost 23,000 lines. So as you can imagine, this can get pretty big pretty quickly depending on the complexity of the scene that you're trying to do. So the Sponza scene, for example, is much, much larger than this and contains many, many objects. It contains almost 400, if I recall correctly, objects. So we're not going to be using that right away. We're just going to be focusing on this one, which is a little bit simpler. So that is the OBJ file. And let's take a quick look at the material file. So the material file gives us a material definition. It gives us also a material count in case we wanted to use that to allocate memory. We're not actually going to be doing that, so we don't have to worry about that. We're just going to handle these one by one. But a new material definition starts off with new material and then the name of the material. And then we have these various properties here, such as Illum, which is the lighting model. We also have the ambient color here. We have the diffuse color here, if we wanted to use that. We have the specular color here. And then we have what's going to be probably the most important for us is a diffuse map, a specular map, and a bump map. Now, how do I know what these different maps are? Well, if I go ahead and let's see, where is that? Let me just open another window here. So if I go to OBJ format specification, believe it or not, Wikipedia actually has a pretty good breakdown of the spec. So I'm not going to step through all of this because I kind of just did that. But it gives us a layout of an explanation as to what all these different fields are. And then down here are materials. Let's see. Here we go. Here's the material definition right here. So this gives us what all the different things are. So Ka is the ambient color. Kd is the diffuse color. Ks is the specular color. And then we have here the illumination map, which is basically, or the illumination mode, which tells us what kind of lighting model we're going to use. We're not going to worry about that right now because we only support Phong. But once we get into PBR, we are going to want to look at that. And then here we have our texture maps. So if we look here, we can see this file here has comments as to what all the various different things are. So the KD is for diffuse texture map. The KS is for the specular texture map, as we've gone over before. We have a specular highlight component that sometimes is used. We have an alpha texture map if we want to use that. We're not going to be using that because our alpha is going to be integrated directly to our texture, our diffuse texture rather, so we're not going to worry about that. We also have something that's an important note here that we're going to have to probably check for. So some implementations of the OBJ format use map bump for the normal map, or the bump map, because bump maps used to be a thing before normal maps were really a thing that tells you how old this format is. But some implementations use map underscore bump, some just use bump. So we have to support both of those cases. We also have displacement map, which we're not doing right now. We may add that in the future as an additional material enhancement, but for right now we're not doing that. And then we also have something in here for decal textures. So that's something we're probably going to be supporting at some point, although maybe not using this directly. So this page is super useful for understanding the format. So I highly recommend you guys take a quick read through it so that you fully understand the format. But anyway, so those are the files that we're going to be working with. So I've added those there. Now, obviously, since we're loading something that is referring to texture maps, we probably should be loading some textures. So in our textures folder, I'm going to be dropping 3 new files. So these are the default material, the albedo, transparency. Now, I should mention that the names of this sort of indicate that it should be used with PBR, or physically based rendering pipeline. We don't have that yet, but we can still make use of these with our pipeline, so that's what we're going to do. And that's one of the reasons I chose this, is because when we get ready to actually implement PBR, this is a nice example of something that's already ready to go. So we're going to use the albedo as just the diffuse map. We're going to use the metallic smoothness. We're actually going to use that as the specular map. And then the material normal obviously will be used as the normal map. So these textures are pretty big, which gives us a sort of idea of what it's going to look like with a little bit larger textures. And so if we go to details here, I don't know if this actually tells us, yeah, it's 4096 by 4096. So these are pretty big boy textures. And as you'll see, it takes a minute to actually load those textures. So we're eventually going to have to address that as well. But anyway, those are all the assets that we're going to need to get building. So let me just get my notes pulled up here. Okay, so we've gone over our material definitions. So before we actually jump into this, there is a couple of small modifications that I want to go ahead and make that are going to fix some issues. So the first thing I'm actually going to do is go into shaders, and I want to take a look at our material shaders, because there's actually a couple of things here that need to be addressed. So one thing that we are doing is when we are calculating our normal, we're just taking the normal that was passed in and we are multiplying it by our model matrix. But the problem with this is we aren't actually normalizing this, which means that this can be greater than a unit normal, which will make the normal map appear really extreme when we actually start, sort of looking at it closely. So what I mean by this is if we actually We might be able to see this if we run now. And I'll go ahead and switch. And I don't know why the frame rate is so low. Might be because I'm recording. I have no idea. But we can see here that the normal is pretty... Yeah, why is that so slow, actually? Let me try doing a post build, and I'll do a clean and rebuild just to make sure. That is bizarre. I have no idea why it's running that way. Let me try turning off the recording and see if that fixes it. I will be right back. Okay, now we're good. So I guess I don't know if it was I don't know if it was browser tabs I had open, but something was causing the GPU just be eaten alive. So I just closed a whole bunch of stuff. I don't know what was up with that. Anyway, so if we go ahead and switch textures here, and we take a look at this from an angle where we can actually see what's kind of going on. This texture is a little bit, the normals are a little bit stronger than I think they probably should be. And the reason for that is because we are not normalizing this. So to normalize that, obviously we just wrap this result in a normalize. And that will keep it within the normal bounds of what the normals should look like. So if we go ahead and switch this again, we can see that in this example, it's not quite as evident, but it is a little bit less extreme. There were some other maps that we would have wound up using in the near future that were a little bit more extreme. And so that was definitely a bug that was bothering me and needed to be fixed. So that is that. Okay, so the first couple changes that we're going to make are in the application. So let's go ahead to application, maximize this, get rid of this, and get rid of this, so we can see what we're doing here. And we will go to right around here where we're loading all of our cubes. So we have here our 3 cubes that we're loading up. And what we're going to do is we're going to actually load up a mesh here. And so the first thing that we're going to do is we are going to create a new mesh. We'll call this car mesh, and we will set that to the app state meshes, and that'll be a sub app state mesh count. And then we are actually going to load a resource. So we're going to need to create a resource loader to actually load models from disk. So this is going to be an example of how we're going to do that. So what I'm going to do is I'm going to write the usage code here first, and then we will go back and fill out all the holes that this creates. So the first thing we're going to do is we're going to say we have a resource, and we're going to call this car mesh resource. And we're just going to set that to an empty object for now. And the next thing we're going to do is we're going to load a resource. So we're going to say if not resource system load, and we're going to pass in a name of Falcon because that's the name of the model file. So that's what we're going to use to determine that. The resource type is going to be resource type. Let's go with, we have static mesh here. Yeah, that should work. We should probably change that to mesh, though, because we're not just necessarily going to always have these as static meshes. So I'm actually going to rename this to just mesh, and rename this to mesh. So the type is going to be a mesh. So we're going to load that, and then we're going to provide the address of car mesh resource. Okay, and so if that fails for some reason, we're going to have a K error, and we'll say failed to load car test mesh. Sure, that's fine. And then otherwise, we will go ahead and take the loaded resource and go from there. So what we're going to wind up with when we finish loading this resource is we're going to wind up with an array of geometry configs, which we already know how to deal with, right? So it's going to look very similar to this code up here, only instead of us generating the configuration, it's going to be generated by a file. So what we're going to say is geometry config. That's going to be a pointer because it's going to be an array, and we'll say configs. And we'll say that is equal to the car mesh resource dot data, because that is what the data for that resource is going to hold. So that is obviously going to be this type. So we're just going to cold cast that because the resource data is just a void pointer. And so we have an array. How do we know what the number of geometries for that is? Well, we are actually going to set the car mesh geometry count equal to the car mesh resource data size. And this data size typically can mean bytes, but it can also be used to mean whatever we want it to mean. So in this case, instead of using it to declare bytes, we are actually going to use that to declare how many geometries we actually have, because our loader will actually be smart enough to free that data appropriately. So we'll go ahead and use that. And then we'll go ahead and set the car mesh geometries to we'll go ahead and actually k-allocate. We're going to take the size of geometry config. We'll multiply that by the car mesh geometry count. Oh, I'm getting used to a new keyboard here, so pardon my typing issues here today. And of course, we are going to memory tag array this. Array. Okay, so we're going to allocate a new array for this because we will not have the geometries array when we destroy the resource. So we don't ever want to hold on to the same array as the resource because the resource gets destroyed once we actually are finished loading the file. So what we're going to do is we're going to set up a new array and take a copy of that data instead. Oops, and I just actually realized that's wrong. We're going to take the data and load our geometries from it, not the geometry configs, because we don't need to hold on to the geometry configs anymore after this. So we're going to have an array of geometries, not geometry configs. And so what we'll do here is we will loop through u32 I equals 0, I is less than car mesh geometry count, and then we'll say plus I. Oops, plus I. And for each one of these, we're going to say car mesh geometries we'll say sub I equals geometry acquire geometry system acquire from config. And we are going to take the configs sub I. And the auto release for this we're going to say is true. Okay. And I believe, let's see, we have and in fact, there is one more thing we have to do before this. So what I'm going to do because so we're going to be acquiring this from config, right? But our config doesn't actually have any tangent data. So that was one thing that we had talked about that we were going to need to generate, because we only have position, texture coordinates, and normals. So we actually are going to have to generate our words. Going to have to generate our tangents for the geometry as well. So we'll say geometry generate tangents, and we are going to pass the vertex count. So the vertex count is going to be, you know what, we're going to actually need a pointer to this, because this is going to get really verbose if we don't have that. So I'm going to say geometry config pointer C, and that's going to be set to the address of configs sub I. That way I can say C, and we can say vertex count, and then it wants the vertices, so we can say C vertices, and then we want the C index count, C indices, and that will generate our tangents for us. And then we can go ahead and set the geometries sub I equal to the result of acquiring from the config. So with that, that is going to generate our geometry for us once we have the loader in place, of course. And then after we're done looping through that, we need to go ahead and set up a transform for the car mesh. So we'll say car mesh transform equals, we'll say transform from position, and we will create a position. We'll have to cast this to vec3, vec3, and we'll use a position of, let's do something a little bit different. So we'll say 15.0f, 0.0f, and 1.0f. And that should position it away from our cube so we can actually see what is going on here. So now that we have that, of course, when we have a scene, eventually down the road, we'll parse this from there. But for now, all we need to do is take the loaded resource and go ahead and unload that. So resource system unload, and we are going to pass it the address of the car mesh resource. That makes sure that the memory for that is freed. And then, of course, we will say app state geometry. No, I think it was mesh count, not geometry count. Yeah, mesh count plus plus. Okay, so that's saying, yes, now we have another mesh loaded. So this is a test mesh loaded from file. Okay, so this is what the usage code for that looks like. It's pretty straightforward stuff, I think. And the idea here was to keep it as simple as possible. Now, eventually, we are actually going to have some sort of wrapping mesh system that we can sort of put all these calls into and then just make one single call to load up a mesh. But for now, this is the way we're going to do it because we don't have that system yet. Okay, so that is actually all we need to do for right now in the application. So I'm going to go ahead and move on. There are a couple of things that we're actually going to have to add to our KString library because there are some things that we're going to need to be able to do as we are parsing the model and material files that we currently do not have. So let me just look at my notes here. So this is going to be an example of something that I'm going to copy and paste because there's not much value in coding this stuff live on screen because there's a lot of repetitive stuff and it really just doesn't add that much to it. So I will explain it though and exactly what it's doing. So next to our equal I, we are going to paste a couple new definitions. So we have something for a case-sensitive equality check between strings. However, it's limited to a given length. And that will basically prevent us from checking really, really, really long strings as this one would do. So we have a case-sensitive version of that and a case-insensitive version of that. And after that, we are going to have a bunch of new utility methods. Towards the bottom here, let's see, we'll probably put it in, where is our split array? Yeah, it is at the bottom. Okay, so we'll go ahead and put the rest of these at the bottom. There's a bunch of them. So we have the ability here to append a string. So that's something that we're going to wind up having to use a lot. And so we have a method here to do that, to just append one string to the end of another. We also want to be able to append an integer or a float or a Boolean, a character. And then we also have a couple of string directory utilities here where we can extract the directory from a full file path. We can extract the file name from a full file path, including the extension, or a file name with no extension. And we can get that from the full path. So we're going to need all of these things at some point in the near future. So I'm just going to go ahead and add those now. So we'll need to go to KString.c, and we'll need to add the definitions of these things in the relevant places. So the first thing that I'm going to do is add the equality checks. So that was down here right after the equal I. We're going to paste the definitions of these two things. So the n-equal for now just uses strncomp, and it's just a pass-through for that. We may eventually wind up actually rolling one of our own of these, but for now, I just don't find it necessary. When we get ready to build out our full string library, that's probably when we'll handle this stuff. And then the strings n-equal I, unfortunately, because of the differences in compilers, we actually have to check for GNU-C and use strn case comp, which basically is a case insensitive comparison that could be used on Linux and Mac. Otherwise, we are going to use, if we're using Visual Studio to compile, we want to use _strni comp. And they both basically work the same way, it's just they're called different things. So unfortunately, that's a platform specific thing. I hate that kind of stuff, but it is what it is. So the next thing that I'm going to do is I'm going to slam in the definitions to all of the functions that we just discussed down at the bottom. So we have our split array here at the bottom, so we're going to slam all these in here. And so, as you may have guessed, at least for right now, appending a string is basically just going to use sprintf, right? And we have our base string here, and then our source string there. We're using sprintf for all of these things. So they all basically work the same way. It's just this token in here changes depending on what you're actually passing through. So we have one for int, float, bool, and character. Directory from path takes the length of the path. It iterates the string backwards and basically finds the last index of a forward or backward slash and says, okay, take everything that is before that and output it. So basically gives you the full directory from the path. The file name for path does basically the exact same thing. It iterates the string backwards, only this time when we find a slash or a backslash, we actually copy everything to the end of the string. And then, as you might have guessed, the no extension version of that does the exact same thing, only this time it looks for the period in the file as well as the slash, and then uses the information gathered from those to actually string mid that and give us the actual result from that. So not terribly complicated stuff, but not something I necessarily wanted to do live because that's not really the point of this video, and I think you guys can all kind of figure out the way that that works. All right. So what is the next thing I have in my notes here? So our geometry utils actually is going to need one more thing. So let's open up our geometry utils H. So right now we just have generate normals and generate tangents. And we are actually going to need one more thing added to this. And I'm going to paste the definition of this as well because it's a little bit lengthy. We are going to need some way to deduplicate vertices. And what I mean by that is one thing that the OBJ format does not handle at all, frankly, is it does not detect when vertex information is actually repeated. And so we wind up being in the situation where we have lots of repeated data in the OBJ files that we load. And it's basically a vertex that has the exact same positions, the exact same texture coordinates, and the exact same normal, which means it'll also have the same tangent when we generate that. And so what we want to do is we actually want to do a deduplication pass where we take any of those duplicates out of that list and change the indexes to go to all the same vertex. And that will actually wind up saving us a lot of space when we actually go to upload that geometry to the GPU, especially on really complicated meshes. However, the way that we're going to do that is not going to be a fast way of doing it, but it definitely works. So ideally, vertex deduplication is not something you want to do during runtime. We are going to be doing that here, but eventually when we set up our tooling pipeline, this is something that we're going to want to convert and handle ahead of time outside the engine. And as we load in that resource, we are going to want to already have that process done so that we don't have to wait on it. So this is temporarily going to be run during runtime, but eventually we're going to be changing that. So with that, I'm going to go ahead and also slam in the definition of this because, again, this is not something that is terribly complicated, and it works pretty much as you guys might expect. So I'm going to go to geometry system.c, and I'm going to go to the bottom here and slam in the definition. So we have a couple of utility methods here. And actually, we have one more that I missed. So I'll put that here. Okay, and we are also going to need to go to the top of this file and, wait a minute. Do we not have the float epsilon? We do. Okay, I guess Visual Studio is just... VS Code sometimes isn't the quickest to pick things up. Anyway, so we have these new methods. We have one for vertex 3D equal. And this runs a vector3 compare that we've already defined elsewhere. And this takes in the position of the vert 0 and vert 1 and compares them to see if they're within tolerance of the float epsilon. Because you can't do a straight equality check on floating point numbers because there's rounding errors, this is the way that we have to do that. So we have to do a comparison against the position, normal, texture coordinate, color, and tangent. And as we add things to Vertex 3D, we'll need to add that here as well, because if any of these things are different, we should not be deduplicating it. So we need a method in here to sort of handle that for us. And it looks like vector3 compare is actually what doesn't exist. So let me see. We don't have kmath in here, which is probably the issue. So let's go ahead and include math, kmath. And that should give us our definition. Okay, so we have the vertex 3D equal. Then we have something for reassigning an index. And so what this does is it basically iterates the provided array of indices. We have an index count here of that as well. And it basically says that anything that is the index of from, remap it to 2. So anytime that we find a duplicate vertex and we remove it from that list, what we're going to do is we're going to take anything that is matching that vertex ID or the position in that array, and we're going to remap it to whatever we tell it to. And that will allow us to correctly remap all of our indices to the deduplicated vertex index. And then every time, obviously, we remove something out of that vertex list, that also means that we are going to have to pull in the ID of any index that's higher than the one we're remapping by 1, because there's one less entry in the vertex array. So that means that we have one less entry. So anything that is beyond that, we're going to have to pull that in by 1 in order to have the correct indices for those things, because now they're one less or one forward in the list than they were before. So that's what this does. And our geometry deduplicate vertices basically creates a new array for the collection to sit in. So this is going to be the new list, and it defaults to the worst case scenario of having the exact same number of vertices. So it uses the vertex count and allocates to vertex 3D, size of vertex 3D rather, and it just basically creates an empty array for us. And then we also zero out the out vertex count. And we also keep a running counter of how many we've actually found, how many duplicates we've actually found for reporting purposes later. And then we loop through each vertex. And we say found here. And we basically look through our out unique verts array. And using our out vertex count, we loop through that collection and say, if there are any vertices in this unique vert collection that matches the vertex that we're currently looking at, then we need to go ahead and deduplicate. And so what we do is we go ahead and reassign the index. We say that we found something. We increment the found count, and we go ahead and break, because we don't need to look any further this time. We're going to actually have to move on to the next vertex. And because we have already included that found now duplicate vertex in our unique verts, that means we don't have to add it. So we can actually just break out of this and move on to the next one. So we say here, if that was not found, in other words, we get through the entire list and we've not found a duplicate of it, then that means we need to hold on to it. And so we go ahead and we copy it over to the unique. And we do that by taking the by dereferencing the pointer to out vertex count, and we set that to vertices sub v, and then we increment the out vertex count. Now, we then go through and we allocate yet another vertices array, right? Because we have unique verts here, but this is going to be too big, because this is the size of the original vertex count, which we may or may not want. We probably don't want that. So we're going to allocate a new vertices array at the correct size of the counter that we've been incrementing the whole time. We're going to go ahead and copy over the unique. So that's just a straight memory copy to out vertices from unique verts, size of vertex 3D times the number of verts we have. And then we're going to destroy the temporary array. So what this does is it basically recreates this vertices array. And then We have our removed count here, which is our original vertex count, minus our out vertex count. And now we can say our geometry deduplicate vertices removed X number of vertices, and then it gives us the original number and the new number of vertices. So this is just a quick way for us to see in the logs how much we're actually saving from this. And you guys will be surprised to know how much that will actually save. So that is all we need to add for our geometry. Whoops, I just realized I added that to geometry system, not geometry utils. So let me back that out and open geometry utils.c. Go to the bottom. That is why I was missing kmath in the other place. So let me undo that change as well. So yeah, this should not need to be there. We shouldn't have to change that file at all. Okay, sorry about that. So yeah, so that is our deduplication taken care of. Okay. One thing I also noticed in our kmath.h is we have a vector 2 compare. We have a vector 3 compare. But we do not have a vector 4 compare. So we are actually going to need to create that because at some point we are going to have to compare vector 4s. So I'm just going to slam in a definition for that. Let's see. So I'm going to do this right before we get into matrices. So that is going to be right here. And all this does, this works the exact same way as the other two functions. It just has one more check for the W component. So we'll go ahead and get that in there. Might as well. And let's see. Just look at my notes here to see what next changes I'm going to have to make. Okay. All right, so there's actually going to be one thing that we need to do, and this is going to prevent problems for us in the future. And I think it's actually going to prevent problems for us in this video too. So our renderer front end, right now we have in fact, so our apply instance right now basically always applies, even if we already have more than one object using that material instance. And this is going to actually be a problem for us when we actually go to load a second mesh that uses the same material instance as something else. We don't actually want to apply an instance of a material more than once. Once we've applied the material for a given, let me back up and see if I can explain this better. So we have our descriptors at the global level, and we have our descriptors at the instance level. And we're already doing some checks to see, have we already updated this shader for this particular frame at the global level, but we're not doing that at the instance level. And the problem with that is, if we have a situation where we have a an instance that's used more than once, like a material instance that's used more than once, and we try to update that twice, we try to update that descriptor twice in the same frame, it's actually going to throw an error because that's not a valid operation. You can only update it once. And we don't really need to update it twice anyways because we've already updated those uniforms, so there's no need to do that. So what we actually are going to do is we're going to put a flag here that says whether or not we need to update. And the reason that we are doing this instead of just not calling this at all is because there is still something in here that needs to be done, and that is the binding of that particular instance's descriptors, because we do need that for the draw call. So we need to bind those descriptors, but we don't necessarily need to update them if they've already been updated for that particular frame. So what we're going to do here is we're going to add a B8, and we're going to say needs update. And we're going to go ahead and pass that through to the back end, which is going to throw an error until we actually get around to that. And then before I actually move on to the back end, let's go to our front end. And let's see, that was the C file, so I need the H file now. And to apply instance here, we're going to add that to the header file, and we'll say param needs update indicates if the if the shader uniforms need to be updated or just bound. All right, so that is that. We'll go ahead and F12 into the shader apply instance on the backend structure, and we'll add it here as well. And actually, I'm just going to copy the comment here. Okay, so that is that. Let me go ahead and grab this again. And we'll go to Vulkan backend H and apply instance. We're just going to add that here, and then Vulkan backend C, apply instance. We'll go ahead and add that here. So that gets passed all the way down the chain, and that should be, I guess that's still going to bleat about it until I rebuild. It's fine. And so that is going to pass that down as expected. So let's see. So before we jump into the back end of this, I actually want to hop back to the front end real quick and implement our usage of this. And then we'll go ahead and hook it up on the back end. It's actually going to be pretty straightforward and simple, I think. But basically what we're going to do is in our draw frame, we have our begin render pass, our shader system used by ID, apply global, and then here is where we are drawing the geometries. So what we're going to do is we are going to say, instead of not calling this, which technically isn't a valid operation, we are going to take this check and convert it to a B8 needs update. And we want to do that because we always need to make this call. We just might not need to do everything inside of that. Whoops. We might not need to do everything inside of that, right? We might just need to actually bind but not actually update. So this, unfortunately, is also going to require a change to our material system to support this, so we'll have to come back to that in a second. But basically, what this does is it just makes the exact same check. It always calls this method, okay? And again, if we didn't do that, it would cause problems for us in the future. So we need to do it there, and we also need to come down here and do it for our UI geometries as well. So we'll go ahead and do it here. We weren't actually doing this check further up, but we probably should have been. But we never ran into it because it wasn't a problem at this level. And that also means that we are missing our synchronization of the material render frame number here. So we need to go ahead and add that down here as well. That was missing. And that, I don't actually think that was done up here. Yeah, it is done up here. Okay, so that actually should be it as far as the renderer front end is concerned. So with that, I guess let's go ahead and jump into the back end real quick, and we'll fix that up because there's not a whole heck of a lot we need to do to actually fix that. Really all it is when we go to apply our instance, right here is where we're going to be doing it. And you'll notice that we actually had a to-do. So I actually had left myself a note in the comments that this was going to be a problem. So we're going to replace this to-do with the actual code. So if needs update, and then we're going to wrap from here all the way down to here. And I'm just going to format that so we can see the difference. So basically, we're going to conditionally update these descriptor sets. And if we've already done the update, then none of this code will run, but this bind code here will still run. So it was a very simple update, very quick fix, but one that was needed nonetheless. Okay, so that should do it for that. Let me just check my notes here. We've got that. We've got that. We do actually need to make a small update to the material system as well to support this. So let's go ahead and do that. So we'll say material system H, and we really only need to apply it to this here, this apply instance. We're going to add a B8 needs update, and param needs update indicates if the material needs to be updated or just bound. And so we have this. We'll go ahead to the material system C, apply instance, add that there, and let's see. Basically, what we're going to do here is we already we need to go ahead and bind our instance, so we always have to do that. We are going to wrap this code here. So the update, where we're updating all of these, we're going to go ahead and wrap all of that in this if check, because if we've already done it this frame, we don't need to do it again. Okay, so this will check that if needs update and only do this where needed. And then our shader system apply instance is actually going to need an update as well, because we do not take in the needs update. And that is actually what's going to pass that down to the shader. So our apply instance here is going to need to be updated as well. So we'll say B8 needs update. And this is where the renderer shader apply instance gets that from. So needs update gets added there. And we need to open shader system.h, apply instance. That's going to be a B8, needs updates, and we'll go ahead and param needs update, indicates if the shader needs uniform updates or just needs to be bound. Okay. And now we should have all of the pieces actually hooked up the way that we need them. Okay, so let's see. How are we looking for time here? Okay, so this is getting to be quite a long video. I am wondering if I should split this into two. I might actually do that because there are actually a lot of changes that we're going to have to make really before we even start writing the loader. So I might actually split this to a separate video. But let's keep going anyway. Okay, so I think the next thing that we're going to need to do is well, let's go ahead and make a couple of changes to our image loader too, because we actually need to make some changes to the texture system. Because there are a couple of, not necessarily bugs, but things that I hadn't thought about before that need to be addressed. So I'm going to address them there first and just get all this kind of stuff out of the way. So image loader. This actually needs to use the file system. So I'm going to put the file system probably include platform file system, because we actually have a to-do here to try different extensions, and some of our extensions are not going to be PNG. Some of them are going to be either Targas or JPEGs or something like that. So we actually want to expand this a little bit to kind of deal with those things. So I'm going to get rid of the to-do here, because we're going to try some different extensions. So one thing I'm going to do right here is I'm going to define an image extension count. So the number of extensions we're going to try is going to be 4 different extensions. And those 4 extensions are Targa, PNG, JPEG, and bitmap. It's going to go through and look to see if each one of those things exists and then take the one that exists. So the way that this is going to work, and this is pretty straightforward, so I'm not going to code this all from scratch, is we're going to loop through that, look at each one of these, construct a file path based off of the current extension, sub I, and we're going to ask the file system, hey, does this file exist? If it does, we'll say found true and then break. If for some reason we get to that and we do not have a match, we are going to bleat about that and say we cannot find it. Find file this or with any supported extension, right? Because it's not just going to be the last one that was used. So if we do not find that, we are going to call it a failure and boot out. The next thing that I need to do is there are certain circumstances where this fail reason actually gets populated and it shouldn't be by the STBI library. And so that is actually going to cause us problems. So I'm going to temporarily disable that for now and come back to it because this can actually cause some of our texture loading to fail even though the image loaded successfully. So I'm going to comment that out for right now. But other than that, that is pretty much the changes to our loader. It's not terribly complicated stuff, but it is something that we needed to address. The next thing that we need to address is in our texture system. So our texture system has a couple problems that we need to go ahead and fix. So one thing that we have here is we have this sort of default texture name, which we're also doubling as our default diffuse texture, which is not something that we're going to want to do. The default texture probably should be something completely different, ideally like a white texture. And so we are actually going to add a default diffuse texture name. We're just going to call that default diffuse texture name, and it's going to be default underscore diff for diffuse. And then we are also going to, in addition to our default texture here, we're going to add something to that to get the default diffuse texture. So that is that, which means that we also need to go to texture system C, and we need to, first things first, go to the top here. We have our default texture. We're going to need to add a default diffuse texture. And we'll go here, and I'm actually just going to find this, and I'm going to copy the, actually I'm going to copy this one, and we're going to say default, change this to default diffuse. Whoops, got the underscore in the wrong spot there. Default diffuse texture, that's going to return that. Update this, and we have that filled out now, so we can get our default diffuse texture. And then let's see. In our create default textures, we have something here to create our specular texture and our default texture. We're going to need to create our default diffuse texture as well. So I'm going to put that right between these two. And I'm just going to paste this because it's basically the same thing as what we had before. The only difference here is the diffuse map is all white. So it's going to be a 16 by 16 texture, 4 channels, and everything is going to be filled with 255, which is a fully opaque white texture. And so we're just setting out all the properties here that we need for that. Does not have transparency, for example. We create the texture, manually set the texture generation to invalid because it's a default texture. And so that's our way of sort of flagging that. And that is all we need to do as far as that is concerned. Okay, so that should do it for our texture system. All right, so let's go ahead and we need to fix one more thing in our geometry system. Or actually one thing. It's not one more thing because we actually haven't changed this yet. So our structure here for our geometry config is missing a vital piece of information that we are going to definitely need in the near future. And in addition to the vertices and indices, we also need to know the extents and center of the particular geometry. So the center being the center point of that individual geometry, or the origin of it. Center is probably more accurate. So basically what we do is we get the minimum extents and the maximum extents, meaning what is the minimum on the X, Y, and Z axis, and what is the maximum on the X, Y, and Z axis. And that tells us how big it is. And the center is basically just halfway between all of that and all 3 axes. And we'll need this later for doing some detection on distance between the individual geometries, because they won't necessarily be They won't have a transform of their own because you can have multiple geometries in mesh. And the transform of the mesh is used for all the geometries it contains. So we need a way to be able to tell locally what the center and the extents of the individual geometry are. And that's something we are going to need in a future video. We're not going to need it right now, but since we're writing the loader, I don't want to have to come back and implement that later. Okay. So the next thing that we need to do is actually start our mesh loader. And this is going to be the big piece of the equation. So I'm going to go to our file explorer here. We have our loaders, and I'm going to create a new file called mesh loader.h. And our mesh loader is going to look very similar to our other loaders. So as far as the definition of it goes, I'm actually going to just go ahead and slam this in here now. And the mesh loader is basically just another resource loader that handles that particular type of resource. So we have that. We have our create method for that, and that's all that there is to the header file. All the logic is going to, of course, reside in the mesh loader.c file. And we'll go ahead and get our includes. Whoops. That was the wrong one. So I'm going to go ahead and slam in all of the includes that we're going to need, because there's a lot of them, and I don't want to type it manually. So obviously we have our mesh loader H, our logger, memory, string, DArray. We're going to need all these things. Our resource types, resource system, geometry system. We're going to need some math. We're going to need our geometry utils. We're going to need our loader utils. We're also going to need the file system to actually load the file. And we're going to need scanf, so we're going to include stdio here. This is something that eventually we're going to wind up replacing with our own version of that. But for now, I'm just going to leverage that because there's not a whole lot of value in replacing that sort of live coding here. So the first thing that we're going to have is we're going to define a mesh file type. So we have different types of files that are going to be available to us in terms of loading an actual mesh. And for right now, there's going to be two of those. And then this third one here, which is type not found, which is sort of a catch-all for any sort of invalid types that we have. So we have our OBJ, and then we have something here called a KSM, which is a file format that we are going to be inventing. And that's going to be in a future video. But the idea is that we're going to take in an OBJ and convert that to a format that we know and understand in the language, or in the engine rather, and convert that to a KSM file, which stores all of the data that we have in a format that the engine can literally just load in as a binary blob, and bam, we have what we need. And so that's the goal with that. But that will be happening in a future video. We're going to be handling this file type OBJ, at least for right now. So the next thing we have is a definition of mesh file types. So we are going to take the file type here, and we're going to hook it to a string representation of the file extension. And that just enables us to bind those together along with an is binary. So we can look at the format of the file, and we can say, okay, well, an OBJ is not going to be binary, but a KSM is going to be binary. And this allows us to quickly just switch between those in code and be able to tell what we need to do or which set of instructions we need to follow. The next thing that we have is something for mesh vertex index data. And all this is it just holds basically information for a face, or a vertex at a particular index, I should say. And this holds the indices for a position index, normal index, and text chord index. And so this directly coincides with the OBJ that we have here. If we go back down here and we look at the face, this will basically hold this information here. Okay. So that is that. We then have face data, which is what I was referencing a second ago, which basically just holds 3 of those. So again, if we look at this format here, we have 3 of these. So each one of these lines will wind up becoming one of these structures here that has 3 of these vertices, which are these guys here. Okay, and that's basically what we're going to read each line into. And then we have something called mesh group data. And this is a collection of faces for a particular mesh group. Mesh group is basically the object in the OBJ file that we're talking about. So if we have multiple of those, we'll have multiple of these. This is all the face data for that particular object in the OBJ file. So that is how we group that together. And then I'm going to go ahead and paste in some declarations of some internal functions that we're going to have here. So we have the ability to import an OBJ file. So that basically takes a file handle to an OBJ file. It takes a string path to an out KSM file. So when we go ahead and do that, that conversion, this is the path of the file we're going to be writing to. So basically what we'll do is when we get to that point, we will take the OBJ data that we've read, convert it to our internal engine format, and then essentially serialize that to a file that is at this path. And then we have an array of geometry config pointers that is going to be, no, that's wrong. It's a pointer to a pointer, but it's a pointer to an array that is created outside. So it's going to be an array of geometries, a pointer to an array of geometries. There we go, words. And so this is going to allow us to update that array, or that D array. You'll notice I've named it D array because we're specifically going to be using D arrays for this. Process subobject is going to be when we reach the end of an object in that OBJ file. That is what we are actually going to be, that's when we actually need to go ahead and take all the data that we've read from the file and convert that to be a geometry, or a geometry config rather. And so this takes all of the positions, normals, and texture coordinates that we read, the face data, which has all the index data, and then builds a geometry configuration from that. We also have a import OBJ material library file. So because OBJ files and OBJ material files are kind of paired together, we also need to be able to handle that. So this reads one of those files. We have the ability here to load a KSM file. We're not going to be filling that out in this video. We will be handling that in a separate video. We also have the ability to write to a KSM file, and we're going to be passing, of course, geometries to that, a file name, path, etc. So that is how we write out our configuration. And then we have a write KMT file. Now, a KMT is a Kohi material file, if you recall. So this is basically going to also take in all of those material files that we have, or the single material file with multiple definitions of materials in it. It's going to take that and write out multiple KMT files, which the engine can then pick up and load as normal, and then we'll have our materials in the engine. So we're already going to use the file format that we've already declared for our materials, and we're going to leverage that in here. And so that's basically what we're going to wind up building out. Okay, so this video has gone on pretty long, but this is literally the last piece of the puzzle. So I'm going to try and get through this. I'm going to try and get through this now. And if it winds up going too long, I will cut it into a separate video. But I think we can get this done in a reasonable amount of time. I probably am not going to live program this because there's a lot of logic here that doesn't really need anything other than a higher level explanation. So the first thing that we're going to handle is the mesh loader load function. So I'm going to, rather than slamming the whole thing in here, I'm going to sort of discuss this brick by brick, if you will. So this is the implementation of the loader interface to load a particular mesh. And so first off, we're going to do the same thing that we do all the time, is just a sanity check to make sure that the loader was passed, that a name was passed, and that a resource pointer was passed. And if any of those aren't passed, obviously we're just going to boot out. And the next thing that we're going to do is we're actually going to load, similar to how we did in the image loader, we're going to try a couple different file formats. So this looks like a lot of code, but it's actually not as complicated as it might look. So what we have here is a supported file type count of 2, and that is for KSM or OBJ. We create our supported file types here. So the first one that we have in line is a KSM file, and we have a mesh file type KSM, and this is true for binary. And then we have our OBJ, which is mesh file type OBJ, which is false because it is not binary. And so we slam those into an array, and they will be iterated in that order. And so what this allows us to do is, if we have already created a KSM file, which would be faster to load, we want to load that. If we do not have that, then we try to load the OBJ, and this eventually will create the KSM file that we can then load on the next pass. And so that gives us a way to, like if you wanted to update the OBJ file, for example, and you already have a KSM file, all you would have to do is delete the KSM file and place in the new OBJ, and the next time you load it, it will automatically generate that KSM file, and we don't have to do it manually. We eventually will have a means of generating it manually without having to launch the engine as well. But this is also a nice way to be able to do it during the normal load process and not have to worry about another pre-process that we have to do before we can actually run it. So all we do here is we build a file with the current extension, just as we have done before. Check to see if the file exists. If it does, we go ahead and open a handle of that file, store that handle up here, set the current type, so that's here. So that defaults to mesh file type not found. So if it's left at this, that means we didn't actually find a file that's valid to load, and then we'll bleat about that and throw an error. But otherwise, it sets the type according to the given file type and then breaks out of the loop. So if it does find something, we are good to go. If it does not find something, meaning that this is still not found, then we bleat about it and we return false. So the first thing that we want to do here is, since we have a file open, we can go ahead and set the out resource file path. And we're just going to string duplicate this. And yes, this allocates memory. It's fine. It is what it is. We'll know that we have to destroy that afterwards. This is not going to be the slow part of the process, trust me. So I'm not really worried about the dynamic allocation there. The next thing that we need to do is we need to go ahead and set up our resource data. So if you recall before, our resource data is going to wind up being just an array of geometry configs. So we're going to create that as a D array of geometry configs. That way it's nice and dynamic, and we don't have to worry about trying to figure out how much ahead of time before we even read the file, what we need to do. So the way that I'm going to implement this is we have a switch statement here. And technically speaking, we don't actually really need this default case down here because, oh, yes, we do. Okay. So if type winds up being something that is not found or not OBJ or KSM, like we've added a new file type up here, but we didn't necessarily implement a method to be able to load that, this will catch that and basically say, this should have a default, actually. That will catch, that's sort of a catch-all, right? Technically, this won't happen because we would have booted out here, but I'm putting it here just to be safe. So if we have an OBJ, we go ahead and we generate the KSM file name. And what we do here is we build out a string. So we take the resource system base path, which we're going to declare here in a little bit. we take the type path, which is declared by the loader, the name of the thing that we're loading, and then KSM, which is the extension. And that is going to be the KSM file name. And so we import OBJ file passing the address of the file handle, the KSM file name, and then the address of the resource data that we created up here. And then we go ahead and set the result of that here. Otherwise, if it's a KSM, we just call load KSM file. So we'll come back to that. Otherwise, our result here is going to be false. And if the result is false, of course, we are going to bleat. So to round this out down here, we are going to make sure that the file is closed. And then if the result is false, it'll say failed to process mesh file. And then we'll make sure to destroy the resource data and zero out the data and data size before returning false, just to make sure we don't leak any sort of memory or anything like that. Finally, we will go ahead and set the pointers. If we've been successful to this point, we'll set the data to be the resource data, the out resource data size to be the length of the resource data array. And that's how we go ahead and set that up. And so the other side of the resource loader that we saw in the application, we'll be able to take a look at this and understand how to use that. So this is sort of the other half of that. So the other thing that we should do right away is define our mesh loader unload, which is pretty basic. All it does is get the count of the D array, and then goes ahead and disposes all the configurations looping through that, and then destroys the D array itself, zeroes out the data and data size. Nothing too complex there. Next thing we'll go ahead and stub in here is the load KSM file, because we actually do need a definition of that, even if we aren't going to do anything with it just yet. So for now, I'm just going to return true and pretend like we did it, which doesn't actually do anything, because all that really breaks is the fact that we don't actually have a KSM file to load the next time around. We'll just have to load the OBJ file every time. Next thing we'll stub out is write KSM file. Again, we're going to handle that in a separate video. So this is also going to return true. So we can go ahead and call it and scaffold all those things and get the calls in place so that all we have to do is drop in the logic afterwards. So this is the writing of that. And next, we actually have the importing of the OBJ file. So this is what that looks like. I don't know why the IntelliSense is flaking out on me here. Let me reload the window. Okay, whatever. There it goes. Okay, it's still kind of, oh, because I missed a slash there. All right. So here is the import OBJ file. This is where the meat and potatoes of everything is. So again, I'm just going to kind of explain this as we go. I'm not going to live code this because I think you'll see that it's not really necessary. So we create new D arrays, and we use D array reserve here for positions, normals, text chords, and groups. And I've chosen the number 16384 here because that's a very large size to go ahead and set up. And this keeps us from having to resize that and reallocate a bunch of times with a really small array, because most objects are going to have a very high amount of vertices in them. And so this will keep the number of those resizes down so that we technically don't have to worry about it. These will be destroyed by the time we're done loading anyway. So yes, it technically wastes a little bit of memory for the short amount of time we're loading this, but we get a performance increase by not having to constantly resize the array, especially when it's at a smaller size. The faces, so this is actually, that's groups, not faces. That comment was wrong. So the groups is basically our mesh group data, which contains faces. We are going to start that at a relatively small size of 4. And again, that's just to kind of keep from having to reallocate for like 1 and then 2 and then 4. You know, we can kind of skip a couple steps there. But we're not generally going to have a lot of OBJs that have huge numbers of objects in them. We are going to be testing that case, but it's, the average case is probably not going to have that many. So the next thing that we're going to do is we are going to cache a material name. So that's just going to be an empty string that could be 512 characters long. And then the next thing we're going to do is set up a couple more things here. So we have the name itself of the individual OBJ. We have the current number of material names. So this is using a U8. Which is going to be limited to 255. I think that's a reasonable limit. I think if you have a file that has more than 255 materials in it, that's a little insane. You might want to split that up. And then we have a list here of material names, which this actually is limited to 32 strings that of 64 characters long each. So we could play with this if we need to. I don't think we're really going to need to, but if you guys ever need to extend the size of this, that's where you do it. So you could basically extend this up to 255 and be safe. Anyway, the line buffer is basically going to be a 512 character string that we're going to read the current line of the file into every single time. And we are just grabbing basically a pointer to that here, which is basically a pointer to the first character in that line buffer, because we're going to need that for a few operations. And then the line length of the current line will be kept here as well. We are also going to keep track of what the previous first characters on a line are. So we're only going to track the first two characters on the line, because that'll generally give us enough information to be able to determine what we're actually going to be dealing with on that particular line. But we actually will need to, kind of look backwards on occasion to see that. So the next thing that we're going to do is we are going to have a while true loop. And I'm normally pretty against these, but in this case, it's basically we're going to be iterating every single line. And we're going to immediately check if file system read line returns false, then we're going to break. Now, I could put this in the while loop, but I wanted this here for debugging purposes, because it makes it a little easier to debug if you need to set a breakpoint on that. It's just a little bit easier to understand what's happening here. Okay. So the very first thing that we're going to do in here, after we've read the line, is we are going to skip blank lines. So if the length is less than 1, we're just going to skip the line. Next, we're going to go ahead and take the first character of the line, which is going to be line buffer character 0. So we're going to take that and examine it first. So for that, we're going to have a switch, on the first character. And this is basically what's going to give us a lot of the information that we're going to need in terms of processing individual lines. So here we have a case for a pound symbol, and that basically indicates that that line is a comment. So I don't remember if, I think this example did have, yeah, so see, we have this free text information up here that we don't really want to process. So we want to skip those lines, and that's indicated by a pound symbol there. So if we have a pound symbol, we're going to go ahead and skip that. The next case we're going to look at is the V case. And the V case is basically going to handle several different cases. So we have the V lines themselves, which is the vertex position. We have the VN, which is the vertex normal, and then we have the VT, which is the vertex texture coordinates. So the V here will tell us that it's one of those things. And then we need to go ahead and grab the second character and examine the second character to see what that is. So we'll take a look at the second character, and we'll know that if the second character is a space, for example, then that means that we are dealing with a vertex position. And what we do here is, for a vertex position, we go ahead and create a vector 3. We go ahead and create something to read the first couple characters of the line into. And then here's where we use scanf. So this basically takes a character string, which is our line buffer, that's our full line, and then a format string saying, okay, well, what do I, how do I read this string? So we're going to read the first thing as a string, and that's going to be the first couple characters of the line. And then there's going to be white space, and then there's going to be a float, followed by white space, followed by a float, followed by white space, followed by a float. And so we're going to take the first string here, jam that into T. That's only going to be a V. And so we're going to throw that out. We don't care about it, but we have to read it into something. And then it takes pointers to whatever it's going to read for the other fields. So here we're going to pass it the address of position X, followed by position Y, followed by position Z. And that is going to take the text of that line and feed it into position. We then take that position and push it into the positions the array. So as you may have guessed, the other cases work pretty much exactly the same. So if we have an N there, then that means we're on a VN, vertex normal. So it just reads that into a normal, pushes that onto the normals array. And if we have a T, then we're dealing with texture coordinates. And so we just read that into a vertex, or a vector 2 rather, and push that into the text coords. And basically, that takes care of that switch. So we have this case here. We do need a break at the end of it. And that is basically our vertex data. So we have, that's how we're going to process our vertex data. Let's see. So the next thing that I mentioned is there's going to be a case for S. And I'm just going to put a placeholder here that does absolute nothing. It's just going to immediately break on that. Just in case we actually decide that we want to handle that down the road. But for right now, we don't need to care about the S type. The next is case F, which is for a face. So we'll go ahead and put a break here. So a face, just for reference, looks like this, if we recall. So we have position, texture coordinate, normal, position, texture coordinate, normal, position, texture coordinate, normal. So there's 3 faces on one face line. So what we're going to do is we are going to create a mesh data face. We're also going to create a garbage array just to throw the F into, because we're going to be using scanf again. We also need to keep a normal count and a text coord account so that we know where these things are actually going to sit. And then basically we're going to say if our normal count or our texture coordinate count is 0, then we're going to read this directly into face vertices 0, 1, and 2 respectively. So we're going to read those as integers here. And we're going to read it into the first, second, and third vertices within this mesh data. Because remember, so we're basically reading position, position, position. Okay? And then, so that tells us how to deal with that. And this normal count and texture coordinate count basically tells us whether or not the OBJ actually contains normals and texture coordinates, because you can export an OBJ without those things. And so this only will handle the positions of those things. And then the texture coordinates and the texture coordinates and the normals will not contain any data. So the other case, which is the case that we're most likely going to run into all the time, is where we do have that data. And in this case, we're going to run scanf, and we are going to we're going to process this as expected. So we may have a face line that looks like this, right, instead. Or I guess it'd be 1, 2, and 3 in this example. So we can have a face line that only has position information, or we can have a face line that contains all of it. Or technically we can have any combination of those things, but we're not going to support all of that. So what we're going to do is we're going to just say one or the other. If we have normal counts or texture coordinate counts, we'll support it. If not, so be it. So basically, our scanf here basically just reads this all the way across and then uses this to set the vertices position, texture coordinate, and normal for that particular face. I hope all that makes sense because there's a lot going on here. I understand that, but you can see that the code is not particularly complex. It really just is. It's pretty straightforward. It's more of a volume of code than complexity. So in either case, we are going to want to create a group index, which is going to be the length of the groups minus 1, and then we're going to push the group's faces into, we're going to push into the group faces, rather, this face. So that's basically adding the data to the faces array of the current group that we are on, which starts off at 0 and increments every time we start a new group. Okay. So that is all of the information in regards to the vertex information. So now we're going to start taking a look at a little bit of material information. So this is going to go here. Oops. So we have a case M. And in this case, the only line that begins with M is material library file. So we're going to go ahead and scanf read in the material library. Okay, so that's the substring there. So we have this, which is going to be the material library, and then this is going to be the actual material file name, which we'll read in here. And I'm going to put a note in here, because we should probably, whoops, an extra slash there. We should probably verify that the string that gets put into substring is material library. So we should probably verify that, but I'm not going to bother doing that for right now. I don't think that's really going to be a case that we run into, but I put a note there just in case we do. All right, so that is the material file. Now, the next piece of this that is it's using the material. And technically this is not the next thing that can occur in a file, but it's the next thing we're going to kind of group together here. So basically the use material line will tell us what we need to assign as the material name. So anytime there's a use material, we are going to assume a new group. So what this means is that we are going to have a new group. We are going to push. We are going to create a new D array for that and push the new group into the D array of groups. So we're going to set that up, and then we're going to read the material name, and we are going to set the material names for the current material name count to whatever we read out of there, and then increment that. And so this will just allow us to sort of keep track of those material names. We need a break here. All right, and so the final case, and probably the most complicated case that we're going to handle, is one of changing groups. So that is going to be the case for G. So this means that we have a new object, and that anything that we have previously read in, we need to go ahead and process as its own mesh configuration. So the first thing that we're going to do is we are going to take a group count of the current number of groups, and we are going to process each group as a subobject. So each one of these will wind up being a separate geometry configuration. And so in that, we'll go ahead and set up a new geometry configuration. We'll call that new data, copy over the name. And then we'll say after that, we'll say if I is greater than 0, meaning we're past the current we're past the current group. We're going to say new data.name. We're going to append to that the current index. Okay, and that's just to avoid running into any sort of duplicate issues. And then we'll go ahead and copy over the material name. Whoops. Okay, so that's the material name copied over there. And then we're going to call our process subobject, which we've not filled out yet. But basically this passes in the array of positions, normal, and texture coordinates, as well as all the face information that we've constructed, and a pointer or the address of the new data here, the geometry config. So this is what's going to set up our geometry config for us. And then what we're going to do is we're going to set up, after that has processed, the vertex count and size and the index count and size for that new data based off of the new data vertices and indices that are passed in. So once this has been processed, we'll know how big these things are, and then we'll go ahead and set these. Next, we will push this to the out geometries D array. So that's where that is done. And we will, of course, increment the number of objects, and we will destroy the current group faces D array. So that way we don't leak that memory. And then we'll go ahead and zero out the material names sub I as well. After that, once we are done processing all these sub-objects, we'll go ahead and make sure that the current material name count is 0. We will clear the groups array. We will zero out the name. And then we will go ahead and read the name of the next object, because that's going to be the first thing that actually comes up. So we'll go ahead and read the rubbish here, which is just going to be the G. And then we will call scanf, and we will go ahead and read that to the name. And that is it for that switch case. So after we have our last and final end of the switch right here. So if we scroll back up here just to make sure we're looking at the right one. At the end of this switch case, we are going to go ahead and set the previous first character 1 to the previous first character 0. So we're basically moving that up 1 in the array. And then we're going to set the previous first character 0 to the first character, the current first character. And what that'll do is it'll just kind of keep moving those characters along in that array and cycling them out as we continue through. Okay, so this is the end of each individual line here. Now, the thing that we need to do is we need to also perform this similar logic when we get to the end of the file, because at the end of the file we're not going to have another group label for us to say, okay, we found another one, so go ahead and save off the current one, then start a new one. What we're going to wind up with is at the end of the file, we will not find a group, but we still have all of this other stuff loaded for the current group that we're on. So we need to actually flush all of that out as well to the group. So this is basically the same logic that happens up here, so I'm not really going to go over it again. The only real difference is it doesn't do this. Okay, but otherwise it just creates that new configuration and pushes it to the out geometries D array. So after that, we can go ahead and do some cleanup. So we'll do right here. We will destroy the groups, positions, normals, and texture coordinates arrays. And then from here, we will go ahead and process the material file. So basically what this is going to do is it's going to get the, make sure that there's actually one defined. And if there is, it'll go ahead and get the full path from that. And then it will go ahead and use that to import the OBJ material library file. So it'll pass that here. And if that fails for any reason, we will have an error here. But we're not necessarily going to kill the application from that. Because we can technically run without materials. We could just use our default materials if we have to. So this processes the materials. And after that, as I mentioned before, we're going to wind up with a lot of duplicate geometry because the OBJ doesn't handle that for us. So that is what we're going to do next. So we're going to take a count of the total number of geometries. We're going to loop through each geometry, get a pointer to that. We're basically going to spit something out to the console for now that says geometry deduplication process is running on the geometry. And then we're going to have a new vertex and unique vertex count, an array rather, and we're going to run our new geometry deduplicate vertices on that. We're then going to destroy the old large array and replace it with the deduplicated one. And then we're going to take a copy of the indices as normal, which is a non-D array. So once we get to this part of the code, we actually don't want to be using D arrays because we don't want anything else that looks at these geometry configs to know or care about a D array. We want to use just regular old arrays. So we're going to set up the indices to work that way and copy that over and then destroy the G indices D array, and then set that to our newly created indices array. So it's a little bit of an extra operation there, but we don't need all the sort of weight or the assumptions that are being made about the D arrays at this level. So we go ahead and fix that as well. And then finally, all the way down here at the end, we return the result of write KSM file, which for now does nothing. But the KSM is basically what is going to be the static mesh file, the binary static mesh file that we're going to be creating in the next video. So it goes ahead and writes one of those out and then returns the result of that. And after all of that operation has completed, it's considered loaded successfully, at least as far as the resource is concerned. It still hasn't been uploaded to the GPU at this point. So this is all just processing that OBJ or eventually a KSM file. To get that into the resource. Okay, so that's a heck of a lot, but we're not done. So there are a couple more things that we have to add, and one of those is going to be our definition for our process subobject. And this is, again, not terribly complex. It's more so just a lot of code than anything else. So what we have here is basically we are going to set up a bunch of variables. So we're going to set up an array of indices, an array of vertices, and we're going to just create those as D arrays for now. And we are going to keep a flag as to whether or not an extent has been set for the subobject. We're going to zero out the out data, which is the geometry config we're currently looking at. We're going to zero out the min and max extents of that. We're going to get a face count, a normal count, and a texture coordinate count from these things that are passed through. And we're going to say skip normals is going to be false, and skip texture coordinates is going to be false. Because we actually have the ability to skip those things if we don't actually have that data. So if the normal count is 0, meaning we don't have any normals, then we are going to skip that. And we're going to bleat about it saying no normals are present in this model. So if you try to use any sort of lighting with that, it's not going to work. Next, we are going to do the same thing for texture coordinates. So we're going to say if we don't have any texture coordinates, skip those as well. Next, we're going to loop through each individual face, and we are going to process the data on this face, or I guess technically speaking, we're going to use this to determine our our vertex data. Okay, so what I mean by that is, whoops, I actually missed a step here. So what I mean by that is, first thing we're going to do is we're going to get the data for that particular face, and we're going to look at each vertex for that face. So that's a loop of 3. It's always going to be 3 because we work in triangles, not quads. And then for each one of those, we are going to set up the index data, which is going to be the face vertices sub I. We're going to push the indices for that particular vertex. So that's going to be I plus the face times 3, just so that it has the correct offset. And then we're going to create a vertex. We're going to set the position to the positions index data position index -1. So if you recall me talking about in here, where we have all these faces here that are 1 indexed, this is where that's compensated for. So this negative, or this -1 here compensates for that. So we go ahead and get the position here. I could have done this on one line. Again, I did this for debugging purposes, just to make it a little easier to step through. So we have the position there. And then before we move on, we actually want to check our extents for minimum. So what we're going to do is we're going to check the position X to see if it's less than the minimum extents X, or if the extent has not yet been set. So if the extent has not been set, we're going to use that value right away. Or if that value is less than the current minimum extent, we're going to use that value. So this is a way for us to sort of calculate as we go along what the minimum is on each axis. So we're going to do that for X, Y, and Z. And then we're going to do the same exact thing in the opposite direction for max. So if it's greater than the current max extents, or the extent hasn't been set yet, go ahead and set it. And then after this, one way or the other, our extents will have been set. So we'll just go ahead and flip that to true. And then here is where we deal with the normals. So we say if we skip normals, we're going to set the normals to vector 3, 0. I suppose we could set that to, you know what, let's actually change that. So let's say vec 3 create, and we'll say 0, 0, 1. We'll make it positive on the z-axis, so at least we have some sort of halfway sane normals. So we'll just default to that. Otherwise, we will use the normals at the index data normal index -1. Again, we're compensating for that 1 indexed array value. So we do that for the texture coordinates. I'm sorry, not the texture coordinates, the normals. The texture coordinates will be a vector 2 of 0 because in this case, we might have an object that maybe doesn't have texture coordinates but should have normals. Like maybe we have a cube that is colored that should accept light but doesn't have a texture on it. So we're just going to 0 that out for now. And then eventually we're going to go ahead and try to extract vertex color. However, for right now, we're just going to hard code this to white because we don't yet have a way of handling that. And then finally, we are going to push the vert onto the vertices array. Next, once we have gone through all of the vertices and faces, so down here, we are going to go ahead and calculate the center based on the extents. So we're going to do this for all 3 axes, which is why we have a loop of 3 here. And we'll just use the elements, so it'll wind up hitting X, Y, and Z. And what we'll have here is the min of the element on that axis plus the max on the element of that axis divided by 2. And that will give us the center point. And then we'll go ahead and also generate tangents for that particular set of vertices and indices. So we'll go ahead and do that, and that'll just do that in place. And that is all that we need to do for processing a subobject. So like I said, it's not a heck of a lot of logic, but it was enough where I didn't really necessarily want to live code the whole thing. Okay. So the next bit of this is going to be processing the library file. And I actually have quite a bit of notes here on this, because technically we're processing all of the material definitions in it, and that should eventually account for duplicate materials. So if there's a KMT that already exists when we go to actually process this, we probably shouldn't write that out. But for now, we're just going to accept that as is and just overwrite it. But obviously, you should probably make sure that your materials that you're importing all have unique names so that you don't run into a collision like that. But for now, we're not going to deal with it. So the first thing I'm going to do is output some debug, just saying we're importing the OBJ MTL file. And we're going to go ahead and grab a handle to that. Okay, obviously if that fails, then we're going to bleat about it. We are going to create a material config called current config. And this is going to change as we go, because remember, a material library file contains multiple definitions of a material. And we are actually going to treat this almost exactly the same way as we did the OBJ file. It's just got a different set of data. So the first thing that we're going to do is we're going to loop through every line, fill out the line buffer. Again, we have a pointer if we need it. We will then go ahead and trim the line before we do anything else. We will, in fact, we'll then check to see if the line is empty, and if it is, then we'll go ahead and skip it. We want to do the trim first, just to make sure that if there's an empty space of a line, that that gets trimmed and skipped as well. So the first character, obviously, is the first character of the line. Now we have a switch statement to look at that individual character. And there's only a couple cases that we have to handle here. So obviously, we want to skip comments, so that's the same as before. If the current case is K, then we actually have some various color information that we're going to extract. So we need to take a look at the second color to see what that's going to be, and then switch on that. So the second color, let's see, I think I've got my, there we go. Let's put a break here. So the second character can be either A or D for diffuse, because we're treating ambient and diffuse as the same thing. And so we're actually going to treat them both as the diffuse color. So what we're going to do here is we are going to scanf the line again and put into current config diffuse color RGB, and then this is actually only used by the color shader. So what we're going to do is we're basically just going to always set the A of the diffuse color to 1.0, because we don't really actually wind up using it all that much, at least not right away. In some of our debug shaders and stuff we might, but for right now we don't really. And then the next thing that I want to handle is the case of S. So KS is for specular color. So it basically just operates the exact same way. However, I should mention that we're not actually using the specular color for now. We're not actually going to define this. And I don't know if we're actually going to ever wind up using it, because the specular color should be mostly based off the light, the color of the light, and technically the material itself. But for right now, we're just not going to use this, but we're going to read it anyways in case we decide against that later. Okay, so that is it for the K case. So let's see, let's find this. And break. So the next case is going to be, for the first character, is going to be N. And this only has an NS, and that's the specular exponent. So that tells us how shiny it should be. So we go ahead and read that out to the current config shininess. And then we have M, which is going to be the various maps. So we'll go ahead and handle that as well. So our substring 10 here is the first thing that we're going to read into, and then the texture file name is going to be 512 characters long, and that's going to be read in as the second thing. So whatever the map is, we only have 2 fields there. So we do a string equals here to see if we have map KD, which is the diffuse texture map. And then what we do here is we grab the file name with no extension from the path. So if it gives us a full absolute path or it gives us a relative path, we don't care. We only want the file name. And so what we'll do is we'll take that texture file name without the extension, and we'll go ahead and place that into the diffuse map name of the current config. We'll do the same thing for the map KS, which is the specular texture map. And then the same thing for the map bump, which is the bump texture map or the normal map. And if you recall, this is only one of the cases that can actually hold that bump map information. It could actually just be bump as well. So what we need to do is we actually need to have another case of the first letter for B and say, well, if it's equal to bump, go ahead and read that in and save it off to the normal map name, because we want that saved as well. Okay, so the next case is we have an N, which is basically the name of a material. And that's what we're going to use to sort of mark our boundary from one material to the next. And so we're going to go ahead and read that in as the material name. And then if that is new material, then that means it is in fact a material name. We should probably do this the other way around, but we can't because of the substring. So that's fine. We'll leave it as is. So we're going to hard code the default material shader name. So anything that we load in as a mesh, at least in this way, is going to by default use the shader built-in material. And we may want to swap that out at some point, but there's not really a way to get any of that information from an OBJ file. So it's just going to default to using the built-in material shader. So we're also going to check to see if our shininess is 0.0 exactly, because if it is, it will cause problems with the shader. So if the shininess is 0, we're actually going to default to 8.0, which is actually probably way too strong, but it's something. It's a default. And then if we've hit a name already, we're going to go ahead and write out a KMT file and then move forward. So the KMT file is the material definition file that we will then load into the engine. And then we'll go ahead and reset the current material for the next round. So we're not going to use the material config directly as we load it this way. We're actually going to use that material config to write out to a KMT file, and then the engine, when it actually goes to load this up, will pick up that KMT file and load it automatically. So we're not going to use that here, but if whether or not we've hit the name before, we want to go ahead and flip this to true just to make sure that the next time we hit this, we'll say, okay, yes, we've hit a name before. We need to start a new material definition. And then we're going to go ahead and copy the current config name to the material name. So that is basically the barrier from one material to the next. And that is almost it for this function, I believe. Let's see. So this is each line. So I'll go ahead and mark that here because it's a little hard to see. Okay. So the next thing that we have to do is just like the OBJ file itself, we have to handle the very last material definition that's in this file, because we will not have another name to hit to trigger the creation of another material. So we need to flush out basically the remaining KMT definition. So we're going to go ahead and assign these same defaults as we did up here, and then go ahead and write out the KMT file, and then we're just going to close the material file and return true. And that is all there is to reading that file. Okay, 2 more functions and we're done, I think. So the next function is going to be writing our KMT file. So obviously we're calling this here. We need to actually create the definition or take the definition of that material and write out something for it. So this is pretty much going to be just looking at the properties and writing out strings in a line. So if we take a look at an example of our material config, let's use this guy. We basically just write all this stuff out like this. We have field name and then equals and then value. And this is what we're going to replicate in this function. So the first thing that I'm going to do, set up a few variables. And so we have the OBJ file that this came from and resulting material file sit in the models directory. Obviously, this is not what we want. We want to move up a level and place it back into the materials folder. So that is why we have the S here, which is going to be the directory, the initial directory of the models. And then we're going to go up a directory and then into the materials folder. And then we have the name and extension. So here is where we build that out. So we have string directory from path. So we take the directory and then we have the full file path here. So we save off the directory. That's what goes here. Then we have the full file path here that we're going to build here in just a second. And then let me actually put this right here and space this out. My sinuses are really aggravating me right now. Okay, so we build the full file path taking in this format string that we have here. So we use the directory, the configuration name, and the KMT extension to build out where that KMT file is going to be generated. And next, we open the file in write mode this time. It is not binary. And we go ahead and pass the address of the file handle to that. We go ahead and bleat about it if for any reason that fails, and we turn false, and that'll make the whole thing fail. We go ahead and output some debug, just saying, hey, this is what we're doing. And then we have basically a series of write lines. So I'm actually just going to slam all this code in here because this is pretty repetitive. And I think it'll make sense to you guys once we actually kind of step through it a little bit. So the first thing we do is we write a comment saying it's a material file. And then we write a blank line, and then we write the version. Now this is hard-coded for now. Eventually, we'll probably, as we expand this, we'll probably want to change that. In fact, to do hard-coded version. Okay, and then the next thing is we write the name equals config.name. And then we have, we go ahead and write out that line. And then we do string format again, where we have diffuse color. And we limit each one of these floating point numbers to 6 digits after the decimal, just to kind of keep it concise. So we go ahead and since we're writing this out in text, we have to do that. And so we go ahead and write that out. And then we do the same thing for shininess, just writing that out as a float. And in this case, we're not actually trimming it. I suppose we could, just to be consistent. So we'll do 0.6f. That's what that does. Go ahead and write that line. And then if we have a diffuse map name, in other words, the first character in it is not 0, meaning there's something in that string, then we go ahead and do string format diffuse map name equals blah, 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 diffuse map name, and we write that line out. And then we do the same check for specular and the same check for normal map. And then we also write the shader, which is just going to be the shader name. And then we have a write line for that, and then we go ahead and close the file and return true. So there's not a whole heck of a lot. This is a very simple format for us to be able to write to. We'll be expanding it, obviously, in the future, but for now, that's all there really is to it. The last thing we have to implement is this guy here, which is the mesh resource loader create. And you guys have seen this a bunch of times, so this one I'm actually just going to copy pasta as well, because it's the same stuff we've already seen. All we do is we set the loader type to resource mesh, we hook up our function pointers, and then we set our path to models instead of, textures or something like that. And then we return the loader. And that is all there is, at least for this video, to our loader. So there is one final step, that we have to take where we basically need to now register the loader because the engine doesn't actually know to use this yet. It doesn't really know what to do with it. And so we actually need to tell the engine, hey, we have this new loader that we want you to use. So go ahead and use it. So we need to go to the resource system, if I can type, .c. And we're going to go ahead here and include resources. Wow, I really can't type today. Resources, loaders, and then we're going to do our mesh loader. And then, as you might expect, we're just going to add this to the end of the list here. So we'll say mesh loader resource create. And I believe that is everything that we need to do. So I'm going to go ahead and do a clean on this and do a rebuild. And what did I miss? Implicit declaration of kdebug. Oh, I probably forgot to add logger here. Yes, include. And this is in the math folder, so that's actually going to have to be core logger. Let's build that. Okay, just for, oops, I didn't want to reload the window. I wanted to run task and post build just to be sure. And let's go ahead and launch this. See what we get. Okay, and see how long those textures are taking to load because they're 4K. But we now have something that's actually, decent looking for, a broken car. Again, I don't remember where I found this actual resource, so it's only a temporary thing for me to test anyways. But it does, have pretty decent maps for me to test specularity and things like that. So if I go into the light mode, you can see pretty clearly what's going on here, as well as the normal mode here. It gives us a little bit of a clearer image as to what's going on there. So that is pretty much where I'm going to leave this video for now. I know this was a really long one, but I hope that this format is something that you guys like, because if so, this is the way I will continue to do it. And again, I'm not going to put a lot of time into editing this. I might cut out long blank sections, but that's about it. I don't intend on cutting too much out of these. So anyway, that's it for this video. Thank you guys so much for watching. If you liked it, please toss it a thumbs up. It helps me out a lot when you guys do toss me that. It lets me know that I'm going in the right direction. Feel free also to leave me some comments below. Let me know what you think of this format. And feel free also to join our Discord server, because if you guys run into anything, there's a lot of helpful people on there that sometimes can catch it if I don't happen to be around, or if I happen to see that you guys are running into an issue, I can fix it. So it's a little easier to go back and forth there than it is through YouTube comments. But either way, let me know what you guys think. Toss me a thumbs up if you like it. If you haven't already, consider subscribing, because we have so much more content coming with this engine. We have so many more things to build, and this is really just starting it all off. So thank you guys so much. You know what? I'm not going to end the video, actually. Bonus content. So what I'm going to do, it looks like we actually have a couple of errors here too. Might fix those in the next video. What I wanted to do actually was I wanted to do one more thing in the application. I want to load a bigger mesh that I've referenced a couple of times, but have not yet actually put in. So I'm going to call this Sponza mesh, because the Sponza scene is something that we are going to be using for a lot of our tests. So let's see, let's just rename this. I don't want to rename because that's probably going to affect that too. Geometries. Okay, and then we have Sponza mesh resource, which is here, 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 and here. And Sponza. So what I will do here is in our textures, I'm going to actually drop a whole bunch of things, which is technically already contains stuff that I have, but I'll just paste all of them because there's a lot of textures in here, right? So we have some test maps and stuff in here, but this is a bunch of textures for the Sponza scene. So I've gone ahead and tossed those in here. And then for models, we actually have Sponza, material, and object. So I'm going to go ahead and run this again. And now you guys will see how much our geometry deduplication actually does help. So if we watch this down here, we can now see how many geometry pieces. Oh, I think I forgot to, let's see, why did that not load? What did I miss? Oh, because I didn't change this to Sponza. That's what copy and paste gets you sometimes, folks. Let's try that again. So we have here our Falcon rec being loaded here, our texture maps for that. But now we see all the deduplication that's happening on the Sponza scene. And you can see here how many vertices we're actually saving, how many things we're actually getting removed here. And it's thousands of vertices that are duplicated. And so this adds up to a lot of memory that we wind up saving just by running that. And yes, this process is slow. You can see how slow this process is. And that's the reason that I wanted to get in here and put that in right away so that we don't miss it. It looks like, however, we are missing some texture data. So looks like some of our textures were not found. Sponza roof diffuse. Let's see. Let's go to textures. Sponza roof diffuse. It's a targa. Why did that fail? Let's debug. Come back here. Image loader failed to load file. So apparently let's see what the issue is here. So I'm actually going to put a breakpoint on the error. And I'm going to run again. It's going to have to go through all the deduplication stuff again. So as you guys can see, you don't want to be doing this every time. It takes forever to actually get through that. And yes, there's ways we could speed that up, but we don't want to be deduplicating vertices every time we load. So this is where the binary format definitely comes into play. Okay. So we got this because we don't have any data. Let's see. So what did we actually... I wonder if it just didn't find the file. Channel count 9. That doesn't make any sense. Column B diffuse. So assets, textures, Sponza column B diffuse. So Let's see. There it is right there. Sponza column B diffuse. And I obviously found it, because otherwise we wouldn't have gotten to this point. Because found was true, so it found it here. Oh. I think this is the problem here. Yeah, because this is looking for a PNG. Okay, I see the problem. So we are already doing the full file path here. So this line was actually clobbering that and loading in PNG anyway. So that needs to go away. So we'll run again. Hopefully this is it. Nope. Looks like we still missed one. So let's go up here and see what we have. Do we have any errors in the console? This is super important for you guys to realize, by the way. When you run into an error, this is why you log stuff. Is because in a lot of cases, it will actually help you understand what the problem is. So I don't think, in this case, we've run into any errors yet. So at least we can rule that out. But let's see the call stack. So saying it needs an update. This is looking at the first sampler, so that is a diffuse. The internal data has an image, has a sampler. That looks like rubbish data though to me. And I can tell that because the handle is 0x1, which is not going to be a valid address. I can't so much tell on these things, but like the width and the height are bonkers. So let's step up a little bit further and see if we can figure out what this actually is. So needs update is true. So all these things would have been applied. Which material is this? We have a normal map. Looks like we do not have a specular map because there's no texture here. Oh, I'll bet I know what it is. So, okay. So we don't have a texture here. So this is a problem because, and this was actually one thing that I had forgotten to fix. So we have, my dog is wobble snoring. Hey buddy. No, he's out. Okay, so if you hear wobble noises, it's my dog sleeping right below my desk. Anyway, this code here is actually going to be the problem. So what we've done is we're actually handling this for the normal texture, interestingly enough, but we're not handling it for the other. So if we have a normal map, in this case, if we have a name that's configured for a normal map, then we're going ahead and getting that. If we do not, then we're using the default. However, for some reason, for diffuse map and specular map, we're not doing that. And then it's trying to load that texture in, and the texture is obviously null, so that's not going to work. So what we want to do instead is we want to make sure the use is correct here, and then we're going to say text system get default diffuse. And this was the reason that I was adding that, is because we didn't actually have this. So we want to do that there, and we also want to do that for the specular map. So text system get default specular texture, and make sure the use is the same here as well. Okay, and that is to catch materials that do not have a definition for the diffuse map. So I'm willing to bet, since we did not get any errors about any more textures failing to load, this was just a simple matter of it not using a default texture as it should have been. So let's go ahead and load this up again and see what happens. I actually just thought of another thing that's going to be an issue, and you guys will see it right away once this loads. Almost there. All right, so there we go. We have our Sponza scene. However, it is absolutely gigantic. And in fact, our clipping plane is actually even taking into account here. It's actually clipping for us because that's how big this is. So I'm actually going to need to go ahead and change that so that we can, sort of view this correctly. So let me go ahead and do that. And I'm still going to have to figure out what this is all about. What are we not destroying here? Oh, I know what that is. We're not destroying the default texture, the default diffuse texture. So in destroy default textures, yep, we are not destroying the default diffuse texture. So that will get rid of those Vulkan errors. But then in application, we are going to need to set a scale for this guy. So we want something considerably smaller. So we want transform, we'll say position rotation scale. And I'm actually going to center this on 0. So actually, I'm just going to say vec3 0, and then vec3 quaternion identity for rotation, because we don't want a rotation. But then we want to create a got an extra parenthesis there. That's what's going on. Okay, and then we want to create a scale for this. So we want to say vec3 create, and we'll just say a scale of 0.05. If I remember correctly, that's what this model has to be scaled to because it's that big. So we'll just do that on all 3 axes. And we'll go ahead and run again. Waiting. All right, we're at the roof, so we're almost done. There we go. So obviously our default camera position is also kind of crap at this point, but what this allows us to see is also that our lights are working against the Sponza model as well. So that is looking pretty good. And this is sort of a more reasonable size that we're looking at here. So I'm actually pretty happy with this. We can see our lighting, our normal maps are working, and we have all these different materials and objects that are all being drawn. And it looks a lot more like a, it's starting to feel a little bit more like a game engine, right? Where we have, sort of a level that we can fly around in and look at different stuff. So obviously we don't have a lot of fanciness going on here yet, but, at least we've got a decent test scene here to look at. So, I'm pretty happy about this. We can still swap out our material like that, and we're still good. And so I think with that, that is actually where I'm going to tie up the video for now. So yeah, if you guys have any questions, comments, please feel free to leave those in the comments below, and I will answer them to the best of my ability. And thank you guys so much for watching. If you haven't already, consider subscribing. Toss me a thumbs up, helps a lot. Click the little bell notification there to get notified as to when the next video in this or other series that I have drops. And I will see you guys next time.